I will be demonstrating is NetSim standard version 9.0. So in order to go to cognitive radio networks, the user needs to select new and cognitive radio networks. So to create a network scenario here in NetSim, there is no requirement of doing any kind of coding. The nodes or the devices are given in this button, so users can select the devices and place them in this environment. So for cognitive radio network, I will be selecting one base station. CRCPE or cognitive radio customer premise equipment. These are the secondary users. So I'll select two CRCPE and I'll connect them using a wireless link. Then to include the primary user, we have the incumbent. Now this is a very basic network scenario of a cognitive radio. Users can also enter some inter-network devices like routers, wired nodes. So now users can also configure each of these devices. Let's say the secondary user 2. So the researcher or the user can specify the IP address, can change the subnet mask, and also the various timeout values like T7, T8, T14. Then in the transport layer, they can set the TCP and UDP protocol and configure. They can specify the congestion control algorithm or the window size. And this specifies actually the device names and the location where they are located. Now for the base station, so users can specify the non-occupancy period, the channel detection time, the false alarm probability, the sensing period, symbols, intervals. So presently the default values are given as per the IEEE standard. Users have the provision to change these values. Now incumbent is the primary user. So here the network designer can set the amount, the frequency range to which this incumbent or the primary user is licensed to. Also the designer can set the operational time, that is how long the primary user will run, and the operational interval, that is how long it will not run. Keep out distance, it signifies the geographic area of its influence. And then the physical layer properties, these are specific to the secondary networks, secondary user networks. So this is the range of frequency which the secondary users are allowed to scan, and as per the standard, the channel bandwidth can be set to either 6, 7 or 8. So even the network designer can change the modulation, the coding rate, the CP factor, the downlink uplink ratio, the interframe quiet period, the bitmap, the duration. So all these properties can be modified from the front end itself. So after designing and configuring the network, users can also now set the flow of data in the network. So let's say node 2 is communicating or sending information to node 7. So in NetSim, we have the option of setting up various applications like constant bitrate, custom, email, HTTP, video, voice, database, FTP, peer-to-peer and emulation. So let me consider constant bitrate. So I will set my source ID as 2 and my destination ID as 7. And if required, the network designer can also change the packet size and the inter-arrival time. So packet size means the size of the packet which is being transmitted, and inter-arrival time specifies how frequently the packets are transmitted. So this graphically a line is representing the flow of the direction of the application, the source to destination. So now let me simulate this network. But before simulation, what I will do is I will enable Wireshark. This I will be explaining a few minutes later. Packet trace, event trace, and dynamic metrics. These are some of the advanced analysis features which a protocol developer uses to analyze his or her networks after simulation. So I have enabled them. Now simulation time specifies that this network, if I create it in the real world and in the real world I run it for 40 seconds. So what will be the result? That is what NetSim will show me now. So this is actually the real wall clock time. So by the time the simulation finishes, let me explain the Wireshark. So Wireshark is a packet capturing software which will capture packets and show all the details regarding the packet. So for example, this packet, it is showing me the data contents of this packet, the transport layer headers, the various flags inside the header, then the network layer header. So I have enabled Wireshark in wired node G. So whatever packets are received or transmitted from the wired node G will be logged here in this Wireshark window. So Wireshark itself provides a lot of analysis like flow graph, which specifies the sequence ID and the destination IDs. Other than that, users can also perform conversations, can check the conversations, can see the various graphs of the sequence numbers, the window scaling graph. So now the simulation has ended. So NetSim provides distinct quantitative metrics at various abstraction levels, such as network metrics, link metrics, then TCP metrics, application metrics, and more at the end of simulation. With the help of metrics, users can analyze the behavior of this modeled network and can compare the impact of different algorithms on end-to-end behavior. For instance, let's say the link matrix, it displays the values of the matrix pertaining to each link, like packets transmitted, then packets errored, then collided, and many more. Similarly, Q matrix, it displays the value of the Q matrix for the devices containing buffer queue like routers, access points. The protocol matrix displays the protocol based metrics. So here you can see TCP metrics, then IP metrics, the OSPF protocol metrics. So this metrics will vary depending upon the type of network simulated. Then the device metrics displays metrics related like ARP table, IP forwarding tables, and application metrics displays the various metrics based on the application running in the network scenario, like throughput, delay, and many more others. The packet animation, it enables the user to watch the traffic flow through the network for in-depth visualization and analysis. So users can get packet details like the packet ID, and the color coding defines some more information. Like a blue line indicates the packet is a control packet which is successfully transmitted. Similarly, a green line indicates a data packet, and a red line indicates a packet which is errored or collided. NetSim also allows users to generate trace files which provide detailed packet information, which is useful for performance validation, statistical analysis, and custom code debugging. For example, the packet trace, the packet trace logs a set of chosen parameters for every packet as it flows through the network, such as arrival time. So you can see here the packet ID, the segment ID, the packet type, whether it's a control packet or a data packet, and if it is a control packet, what kind of control packet it is, then accordingly the source, destination, transmitter, receiver. So almost around 28 columns or 28 tuples of information are present. So users can see the packet sizes at the respective layers. So this is the transport layer payload, or the time at which they reach the layers. To assess the user, Excel has a feature of filtering the packet trace or the Excel files. So users can easily analyze the packet traces. For example, if I want to know which packets are errored, so I can easily select errored, and I can see only those packets which have errored in the network. The event trace records every single event along with the associated information such as timestamp, event ID, event type. So NetSim is a discrete event simulator. So as you can see, starts from the application out, and in the router the OSPF protocol is running. Then you can see from the nodes the physical in, the MAC in. So whenever a packet is going inside up to the application layer, they are called in events, and when a packet is coming out from the application layer to the physical layer are called out events. So event by event the explanation is given how the packet or the events are being performed, and you can also see sub events like carrier sense, waiting for interframe gap, and transmit US burst. Dynamic metrics allows user to monitor the value of a parameter over simulation time. So this is essential for researchers to understand the behavior of a network at any instant of simulation time. So you can see how the throughput was for the wireless link. So these are for each of the links, the data rate through the links. And this is for the application 1 CBR which we are running. And this is the TCP congestion window. So going into the performance metrics, for cognitive radio specifically, some of the extra metrics are added, like CR base station metrics, how many superframe control headers and frame control headers were sent. Then CR CPE based metrics, that is the secondary users. Then the incumbent, that is the primary user based metric, what is the frequency it is using, how much it was operational and how much it was idle. Then this is the channel metrics. So these are some of the extra metrics which are displayed for cognitive radio. So in this manner, users can design a network and then analyze it in NetSim. So just now I have performed the designing cognitive radio networks using NetSim. Now I would like to continue with some more information on cognitive radio. As per IEEE 802.22 protocol, a superframe has a duration of 160 milliseconds. And each superframe starts with the transmission of a superframe control header, that is the SCH packet. Moreover, each superframe consists of 16 frames and each frame is a duration of 10 milliseconds. The superframe control header, it carries the BS MAC address along with the schedule of the quiet periods for sensing as well as the other information about the network. So if we go deep inside each frames, we can see that a frame is comprised of two parts, a downstream subframe and an upstream subframe. So each frame will transmit a frame control header or a FCH packet, which is followed by DS map, then US map, then the UCD and DCD packets. And as you can see here, this is the TTG, that is the transmit receive turnaround gap. So this is the amount of time which allows the CPEs to switch between the receive mode and transmit mode. In cognitive radio, the channels are classified into types which are based on their utilization. So as you can see, if a channel is used by the primary or licensed user, it is classified as a protected channel. If a channel is currently being used by a secondary user, it is classified as operating channel. And if a channel is ready to be used by secondary user but not yet being used, it is classified as a backup channel. If a channel is not used by primary or secondary user and is not yet a backup channel, it is termed as a candidate channel. And finally, channels which are not sensed are classified as protected channels. So if we go to NetSim and in the packet animation, users can easily view the packets being transmitted. So now you can see that initially the superframe control header or the SCH packets are being transmitted. Then the frame control headers. Then the DS map, US map, UCD and DCD packets. And as there is no data to transmit at this moment, so the next frame control header for the next frame will start transmission. So this will go on continuously until and unless a data is there to be transmitted. So as you can see now, a TCP sync packet is getting transmitted. Designing cognitive radio networks using NetSim. Just now I have shown you through the packet animation how the users can check, analyze it. Furthermore, the users can also see these packets using packet trace. So via packet trace, you can see the superframe control header packets are being broadcasted from the base station to node 2 and node 3. Then the frame control header packets are being broadcasted from the base station to the nodes. Then the DS map packets, the US map, the UCD and DCD packets. And this will go on continuously until and unless packets are there to be transmitted from the higher layers. So a typical CR application or cognitive radio application is the opportunistic